Yeah, go for it.
All right, we're about to get started, everyone. We're from Dickinson College. So we're from Dickinson College. We run a pretty small scale operation, making about 100 gallons of biodiesel a week, an estimated 2,000 to 3,000 for the full year. We have interns coming in throughout the year during school session and during the summer. And our primary focus is education, but our in-house vehicles do use our fuel. So the vehicles that are part of our facilities department use the vehicles on campus. The president's car is fueled on our biodiesel. And some of the organic farm equipment also uses our biodiesel. So this talk is about methanol recovery. What is methanol recovery? Biodiesel and glycerin, as you know, contain surplus methanol after you do the transesterification reaction. Methanol can be driven off by heating, and it can be recaptured for reuse. This can be done in your biodiesel reactor if you're not using a plastic reactor, or it can be done in a separate unit based on whatever works best for your shop. And it's really pretty simple. It uses almost the same procedures as making a batch of fuel. Sorry, that's fine. So why would you do methanol recovery? For us, the most important thing is safety and sustainability. When our shop was originally designed, our boss, Matt Simon, was informed that he was not allowed to continue running the biodiesel operation because methanol-laden glycerin is a hazmat and we could not keep it on site. The school would not let us do that. So he immediately set to work creating a methanol recovery system. So methanol is obviously very toxic, flammable, not safe, and doing the methanol recovery allowed us to, one, keep our operation in full swing, and also allowed us to feel safer in our shop and comply with the PADEP. It also simplifies the handling and use of byproducts, especially glycerin. We've been doing a lot of research using glycerin for alternate purposes rather than just disposing it. And the other thing that's really nice about methanol recovery is that it can save you some money and resources. Getting back methanol, you can reuse it in your next batches of fuel. So, distillation basics. This is going to be kind of basic, kind of simple. Basically what happens when you heat up your glycerin is that you're going to start driving off some of the methanol vapors, or methanol that's in your glycerin. It's going to vaporize. The boiling point of methanol is about 150 degrees Fahrenheit. Methanol is highly volatile. It'll vaporize very readily. When methanol evaporates inside the reactor or your closed pot, it causes an increase in pressure and pushes out through the available opening. And usually it's then sent through a condenser. We use a basic water condenser. The water condenser is made up of basically two pipes, an inner and an outer pipe. The vapors from the pot feed directly into the inside pipe, which is generally crimped. The water is passed through the outer pipe in an opposite direction from the way the vapors are flowing. This increases your countercurrent heat exchange. So you're losing heat from your methanol vapors and they're starting to recondense and turn back into a liquid. And then this liquid can be collected at the end of your process. So we use a basic plumber's delight condenser. It's fairly easy to make. And I believe Andrew passed out some instructions on making it. This is actually...
Or on the back sheet there is Graham Lamb's design for the reflux column. Reflux means plumber's delight. which we have more up here.
And it's actually pretty much this image right here. The outer jacket, both are made of copper. The outer jacket is fairly simple to make. It's some basic soldering. This is us making one in a total of, probably it took us about an hour to make it in our shop. And the inner pipe is crimped to allow for better flow design so that you're getting an even temperature throughout and you're allowing the vapors to recondense. The other option for a pretty basic condenser is what we call our booster condenser. It just consists of a single metal pipe that's coiled and hot, which allows for a large surface area. And the larger your surface area is for heat exchange, the better your recovery is going to be. So this particular condenser is actually a cooling coil taken from a dehumidifier. What we do is we just submerge it underwater, hence the large chunk of cement, to keep it in the bottom of this bin. So we just submerge it in cold water, and as the hot vapors travel through the coils, they'll recondense and we'll get a liquid distillate out the other end.
And so what we do in our shop for methanol recovery, we use the standard Appleseed design, and point it on at this point. As you can see, it's tied into our exhaust system, and so that it flows out. We have a chance we can direct it to go outside our shop if we need to vent, just when we're filling or emptying. But when we're doing recondensing, we have it so we can valve it off so it then flows through the plumber's delight. And then we have the water flowing in, counter current, down here, up there, and out. And then on this 5-gallon carboy, this is the proper method of when you go to capture the condensate when it comes out. You want to make sure that you can use almost any kind of vessel as long as it has 2 openings. One opening for it to come in, one opening for gas or air being displaced to go out. And another very important thing is make sure you use hose clamps, because we've had many situations where it just goes and pops off for no good reason, and before you know it, you have methanol in your workspace. And so, one of the other things I want to point out is we have, for our recirculation column, we had a static mixer, which this was made out of plastic. And it got to the point that when we were doing methanol recovery, we were taking up to initially up to 210 degrees Fahrenheit. And this plastic was rated for about 190. And before we knew it, it was already warping and starting to melt. At that point, we had to make a change to our reactor design. And so, this reactor is the current one we were using. We have it wrapped in heater, or the water heater installation. Make sure that we cut back the amount of energy loss just because of the this is heat emanating out. But we also replaced all of the plumbing to make sure it was all black steel, because that way you can be sure that it can handle temperatures, which we now take it up to about 260 degrees. But then going and what we use with the water we flush it through and we use it to do our washing. So when we do recovery, it's going to generate heat, especially when we do recovery on glycerin. And so this wash water goes from tap temperature about 56 degrees Fahrenheit on average. It'll go up to 80, sometimes even 90 degrees Fahrenheit. And we use that water to wash our biodiesel with.
All right, so evaluating the purity of the methanol that you're recovering. So using just a condenser, you're getting back some distillate, and you want to know how much of this is methanol and how much of this is not. So what you want to know is what else could this be? Well, looking at the transesterification reaction, you know that the only other thing that could be boiling out of there is water. So the boiling point of water is about 212 Fahrenheit. We've already talked about the boiling point of methanol being about 150. So during recovery, we raise our fuel above 240, most recently up to about 260 degrees Fahrenheit. And the problem that we were running into was, well, we're passing the boiling point of water and some of that distillate that's coming off is obviously impure because it's watered down. So what can we do to avoid this problem? But even before that, how are we checking to see how pure our methanol is? So just testing, we're doing a small home operation. We're not sending our methanol in, but the most basic way to test it is to do a basic purity test. We're weighing out a liter of methanol, and we're finding out the mass of that liter of methanol and comparing it to a methanol purity chart that we found. It's on the InfoPop forum, and you can find it at a lot of basic chemistry websites. And so we're pretty sure that this is, up to date. It's been tested. These are definitely the purities of methanol at certain weights for a liter of methanol. So we're just doing a very simple methanol purity test to figure out how pure our methanol is. So methanol recovery at the Dickinson shop, here's what we've been doing, and what we've been finding was, that methanol purity, starting at about 160, which is a little above the boiling point of methanol, was fairly high. It was in the high 90s, but as we got up to 190, 200, and above, we were getting methanol purity in the 80 percentile range, which is not exactly pure enough for us to be using it back in our fuel.
Where were you taking the temperature at?
We were taking the temperature both of the reactor, and we were taking the temperature of the condenser, the distillate coming through.
At the condenser, just before the condenser.
But this is based on the temperature of the pot. This is the temperature of the glycerin that's reacting in the reactor. So this is what we were finding, and we wanted to make that a little bit better because after raising it up over 200 degrees and getting this kind of wet methanol, we were coming up with a lot more wet methanol than we could just remix into our pure methanol and use again, which is a simple solution, but when you're collecting 5-10 gallons of it, it's not so easy.
How pure does it need to be to reuse it?
We are basically, we're going by, it's got to be in the 90s, preferably above 95.
In the past, we tried using 50 to 80% purity, and we found that it's detrimental to your end product. But we had to wash it for a fourth time, or settling time was increased. It just didn't work well.
And do you get water off when you're recovering from the biodiesel phase?
Not as much. We're mainly getting methanol in the 90% range.
Do you use sodium or potassium?
We're mainly using potassium hydroxide. We haven't really tried, we haven't really taken data using the sodium hydroxide. Or at least I haven't.
You show your purity on that previous chart there, but what about the percent recovery? How does that correspond? I would assume it's an inverse to that kind of a curve.
Right. I'm going to sort of touch on that a little bit later, but if you have more questions, you can ask me at that point. So, the roadblocks of methanol recovery.
So, hold on. For some reason, I'm not really active on this slide. All right, so with glycerin by volume, there's a lot more methanol in glycerin than with biodiesel. When we were doing, and then because of this, it makes a slight difficulty for doing recovery because you're going to be putting in a lot more energy, and a lot more energy is going to be coming out as well with the large amount of methanol coming out. And so, but the other issue is that, and so because of this, we have to institute alternative methods to make sure that we are able to chill down what we have, our vapor coming out, sufficiently to make sure that we're not just venting hot methanol gas outside our shop, which at that point is a hazard and it's a waste of resources. And so what we found useful was that we put in a booster condenser in line, so you're just extending the condenser essentially, just making it longer surface area. Then we have the recirculated cooling, which is a system I'm working on currently using just a radiator out of a car with the fan attached, and which that fan I have running off of a DC battery, in which it is able to, or right now sufficiently able to cool down the booster condenser to stagnant water by 10 degrees at the moment. And then also the one thing that really helps is having the reflux column, in which that it keeps your purity incredibly high. And so which we'll go into that in a little bit right now.
So just one thing to point out is that booster condenser was, again, just the coiled cooling agent from a dehumidifier. We just added that onto the end of our condenser, our Plumber's Delight condenser, to increase the surface area for heat exchange. So just to clarify that, we were adding a second condenser because the amount of heat that and methanol vapors that the glycerin was generating was overwhelming the 4-foot Plumber's Delight because there's so much more methanol in the glycerin than in the biodiesel. So one of the alternative methods, like Andrew was saying, is the reflux column, and this is probably something you guys are really curious about. It's something we sort of put together at the beginning of the summer, and it's an easy way to kind of increase the purity of your methanol as it's coming out, especially when you're doing recovery on the glycerin, because this allows you to recover and reuse more pure methanol. So basically how this reflux column works is it's placed directly on top of your reactor before you hit the condenser. It allows for what's called fractional distillation. When you boil two liquids with fairly close boiling points, their vapors are more likely to mix when you're doing the distillation. So the column allows the liquid with the lower boiling point to evaporate and rise to the top, and that's the liquid that's the vapor that's getting recondensed and turning into liquid form and collecting, while the other vapors are recondensing inside the column and falling back down. So this diagram sort of gives a alright image of what it looks like inside. But basically, what we're going off of is that methanol boils at 150, 160 Fahrenheit, and water boils at 212. So we packed this column with a high surface area material, and that allows for the condensation of vapors as you travel up the column. So the methanol water mixture starts going up the column, it's evaporating, it's traveling up, and the column allows for a series of vaporization recondensation stages. And as you go higher and higher up the column, your vapors that boil at a higher boiling point, they're starting to cool down, and they can't stay as vapors, so they recondense and fall back down, while your vapors that boil at a lower boiling point make it all the way up to the top of the column and then pass through your condenser. So the methanol vapors are the ones that boil at a lower boiling point, 150 Fahrenheit, and they're going to make it all the way to the top of the column, but the water vapors that are boiling off are going to start cooling and recondensing and falling back down into your glycerin pot. And so that's sort of what this is showing here, is the recondensation of vapors, water vapors in this case, falling back down while the methanol vapors are allowed to escape and pass through the condenser. So this is our basic reflux column design. I'll let you go into that.
So the reflux column itself is actually very, very easy to construct and very inexpensive. This model, we've only been using it with our 80-gallon apple seed. Of course, if you use a 40-gallon apple seed or a custom-built tank that's doing maybe 200 gallons at a time, it's going to be completely different sizing. But what we found is that, as you can see the parts list, just a 2-inch nipple at 30 inches long. It's black steel. We have 2 reducer couplings and to attach it to our top of the reactor. But the main or most important part of this is on the inside. We packed copper scrubby pads essentially. Really cheap, really expensive, and easy to replace when you need to. We've only filled it 3/4 with the copper pads, and this causes a surface area that when you have the methanol vapors rising up, that it causes the water vapors then to condense and fall down because they have insufficient energy to go up. So,
I just want to add something to your last. I just want to add that we also have a thermometer placed at the base of the column, and we have one placed at the top of the condenser. And so this allowed us to tell what our temperature gradient was, and we were seeing at least a 10 Fahrenheit temperature difference between the bottom of the column and the top, which shows that you're definitely getting this fractional distillation. You're getting the lower boiling point vapors moving to the top while the other ones are recondensing. So that's important, is to measure your temperature gradient and make sure you're getting that.
Is there any specific reason that you put it over on the topper side rather than right at the top of the column? I think we want to measure the temperature right at the exit point where your fumes are coming out without letting it travel 2 feet through ambient air and cooling itself.
The placement of that is, the reason why it's placed like that is just because the way we have our pressure release valve set up along with our alternative venting method. And it's more so just that's how it ended up being. But ideally,
Expediency.
yeah.
Ideally, you should have a thermometer placed directly at the top of the column. But for safety issues, we have, like Amy was saying, a pressure cap so that if we build up too much pressure inside our reactor, that'll pop and it'll send the vapors immediately through our vent hose, which takes methanol vapors directly out of the shop. So more of a safety precaution, but we're gonna be fiddling with that.
So when it's actually functioning and water's dropping back out, water then essentially is falling into your glycerin, and that causes no ill effect.
Not that we've found.
We've only done one batch so far with glycerin, and the glycerin came right out. We've had no, we're yet to use it to make soap. We don't know, it might have an effect on that, but it's behaving the same way as our other glycerin has.
Maybe slightly more viscous, but if you get it out at a reasonable temperature, you should have no problem. And we've had no problem with it solidifying during storage either.
How do you gauge your recovery then? When your condensate flow starts lagging, well then you just consider it done? Or is there some of it? Because, well, I guess probably what he was wondering what I'm talking about, the water that you're dropping back in, of course, is diluting your glycerin that you're refining. So when do you know when you reach an end point?
Well, right now, our end point, when the water vapor already in there, it's not really diluting because the water is already in the glycerin to begin with. And the reason we've taken it up to 260, we want to go higher, but the issue then becomes what temperature can the apple seed take? And so we're kind of stuck within just just safety boundaries of not wanting to push something too far before we can really be sure if it's safe. We feel that we could probably take it even higher and still get more methanol out of it, because at 260 the vapor at the top of the stack is still 160 degrees Fahrenheit, and at the bottom it's about 210, 220. And so it's still chilling it down, the reflux is still working, and it's still producing a steady flow of, I think maybe it's like 1/8 of a gallon a minute. So it's still working.
But for safety reasons, we've only taken it as far as 260, and we actually have sent that in to be tested, to be flashpoint tested, which we're going to show the results in a second, but that seems like a safe enough level. We got it to pass the flashpoint test, and it's no longer a hazmat, which means that it's got a very, very, very small percentage of methanol in it still.
How long does that take?
How long does it take? We're still working on timing. We've had a lot of other things going on, so.
On average, before we use the reflux column, it took us about 4 hours to get up to temperature. With the reflux in, it takes us about 5.5. But even then, that additional time period, I feel it pays off because the entire process, we were getting methanol back at 95% plus purity.
Are you heating that just with the elements in the water heater?
Yep.
110 or 220?
220.
Okay.
Right, and so, I mean, this is just kind of a basic display of our performance with the column in terms of purity. The blue is the methanol purity, the methanol recovered from biodiesel, and the red is from glycerin. And basically what we've been finding is we're staying entirely out of the 80% range in terms of purity, and that's good enough for us.
I wasn't here at the beginning. How much methanol are you recovering from batch biodiesel?
Okay.
What is it?
I actually didn't say that. We're recovering from the biodiesel. We run a 50-gallon batch, so we're recovering about 1 to 2 gallons from that. It's been higher since we added the reflux column.
Still 5%.
Right, and we've been running about a 45, 50-gallon batch of glycerin. We've only done one. We've only had time to collect enough to do one. But that's what's shown up here, and we got, I believe it was like 14 gallons back from that 45-gallon batch of glycerin, and that was all methanol in the 90 percentile in terms of purity.
And so we were able to, or my rough calculation was that on a single batch of biodiesel, we were able to reclaim about 5 to 5.5 gallons of that batch. So we're approaching half.
So that's just giving them liters.
Do you need to agitate the glycerin when you've got 40 gallons in there to get the methanol coaxed out, so to speak?
Yeah, we keep it moving. We run our pump for agitation. It's essentially the same as running with or making a batch of biodiesel, keeping it agitated. That way, you make sure that the heat is evenly distributed. You don't have any stratification, and this is a safety issue. That if you have heat stratification, you have a chance of burning out your elements. But we keep it flowing. We've been toying with the idea of changing. Right now, when it comes in, it's just dropping straight down in a column. We were thinking of putting a spray or some obstruction that will cause it to spray, maybe force more vapor out, and might increase efficiency.
Centrifugal pump?
Yes.
When you're getting methanol or recovering methanol out of your biodiesel, is that just during the processing, or are you separating? That's after separation, and then you're doing a recovery from the biodiesel.
Yeah, we separate the biodiesel and the glycerin before doing recovery. We do them separately. And I'm sorry, I gave you incorrect figures. We're getting about 9.5 gallons back from a 45 gallon batch of glycerin. So 9.5 gallons of methanol, which is 35.5 liters. We're still getting more back than we were without the reflux column.
How do you control the temperature? You disable the thermostat in the...
It's right now, it's manual control. We're currently working on working aquastat in, but the current it's a Honeywell aquastat. It's rated up to 240, so we've managed to pick up a Omega heat control system, and it's a very expensive unit just for its purpose too, but it just makes sure that the extra level of safety. This is one of the issues I'll talk about in the safety section.
Right, and so this is just, we pulled glycerin samples at 240, 250, and 260 Fahrenheit after running recovery. And we found that the optimal temperature to take it up to that clears us way beyond the flash point defined by defining glycerin as a hazmat is 206 Fahrenheit. The flash points were 143 Fahrenheit, 140 and 208 respectively for 240, 250, 260. So raising it up to 260 takes us well out of the hazmat range, and we consider that a very good thing because that allows us to do other things with our glycerin rather than just try to dispose of it.
Such as?
Such as making soap, composting. We're doing some composting research, and we're also doing some biogas digestion research.
So, with methanol, you're working with a very toxic, hazardous substance, and safety is by far one of the more important things you have to focus on with doing methanol recovery. Because you're taking the glycerin, especially for our case, we're taking up to 260 degrees. And at that temperature, your methanol is well above its boiling point, way above its flash point. And the slightest spark or any way to set it off, it'll go. And so the issue is safety when you're doing this kind of work. And so biodiesel itself, when we do recovery on it, it's quick, it's easy, and we're able to, we can be a little more relaxed, but even then you still have to keep a vigilant eye on the reactor. We watch temperature, we watch temperatures on the exit stacks, we make sure that it's circulating, we make sure nothing's clogged, and because that way, like if you had a clogging reactor, or a clogging a recirculation pump, you have stagnant oil in there, or stagnant glycerin, you have the heating element still running, temperature stratification, and it can ignite. But with glycerin, especially when the preliminary stage between after you react it, after you make your biodiesel, and what you're going to do with your glycerin, that's what I feel one of the more important parts of shop safety. Is one method we tried, we had a 40-gallon apple seed that after doing a batch of biodiesel, after letting it settle, we would move the glycerin directly over to the little reactor and do recovery using that, in which we would do tandem recovery the following day, so that way it was out, it was recovered, it was clean, it was good to go, and we could store it. Because we weren't allowed, Pennsylvania does not allow you to store glycerin, or methanol-laden glycerin for more than a year on a site. And so we're able to go and just keep the turnover, keep getting it cleaned up, and we can use it to make soap, we do the compost, biogas, and maybe other options as well as we find time to do it. And so the other issues is when you're storing it, if you don't have like the space or just the time to set up having the tandem recovery system, and you have to store it in the item, avoid using plastic at all costs. Plastic can melt, and if you have heaven forbid a fire go off in your shop, plastic will melt, and we'll just add that glycerin and that methanol straight to that fire. And so what we've used is we have a 55-gallon steel drum that we pump it over and we hold it in that. Because when we had our fire marshal come in and look at our setup, it was the main issue we had with our entire system was that when we were storing methanol, we were storing it in plastic, like 10-gallon drums and like paint buckets. And at that point, we had a good 10, 15 paint buckets stacked up in the corner. And it got to the point that we also, the labels would just go and we use Sharpie we write on top like glycerin with methanol and glycerin or biodiesel or some drips on it and wipes it right off. And then we ended up having 10 buckets, we had no idea what was in it. And so by keeping it in a dedicated spot for storing your the glycerin, you can be sure where it is and be sure that it won't be a hazard if anything ever happens. And then one of the other issues, and one of the more important things is also to make sure you have a spill control plan. Because say if you accidentally kick open the valve and it starts leaking on the floor, make sure you have the proper sawdust or the chemical absorbent pads. Make sure you have them on hand so that way if something goes wrong, toss them down. And then, all right, then one last thing is with our methanol recovery, we're taking it to high temperature, and one of the biggest issues is sometimes we make mistakes. We may be halfway through a reaction and have to go to the bathroom, or you might trip and fall. Something might happen in which the operator might be incapacitated. And so one of the issues we're right now working on is working an automatic shut-off system. That was with the Omega controller I got my hands on. I'm working it into the system so that once it reaches pre-designated temperatures, it'll cut off no matter what. So that way it won't continue heating itself up and a runaway reaction. And so working in a buddy system ideally, but working in an automatic system just to be sure that if anything goes wrong, there's something else, another fail-safe to catch it. And so that goes, the Honeywell Aquastats, they're about, the ones we have been using about $100. You can wire into the system. You can use, or I don't remember the exact electrical term for it, but it's essentially a solenoid valve that opens and closes a circuit, and which we're working that in so that way, once it gets up that temperature, closes or opens the circuit and stops it. The Omegas can run up to $200 to $250. Very expensive, but you can work in thermocouple wire, multiple inputs, and you can also have it controlled. You have settings for like when you do not only methanol recovery on glycerin, you also have a set for when you're doing a reaction for biodiesel. You have it cut off at 130 degrees Fahrenheit, so that way it protects you in that sense as well.
Alright, so this is just a diagram of how our shop is set up. For the rest of the presentation, we're going to focus on energy. So I'm going to mention briefly the solar collector that we have and how we're using it, and then the pumps and how to figure out energy balance. So, what is energy? And it's not just something that comes from coffee, although I'd love to think it is. Energy is basically work. Work is force times distance. Sorry, this is going to be about a 5-minute physics lesson. So energy basically is work. If you ask my physics professor, he'll give you some sort of scenario about a mountain. As you go up the mountain, you use more work, you need more energy, or you do more work, you need more energy. This mountain picture. There are different types of energy: kinetic, thermal, potential, mechanical, electrical. Here are some conversions. Power is energy divided by time. So joule is the unit for energy. 1 joule per second is 1 watt. So a watt is a unit for power. And then do a whole bunch of conversions. I did on the train here, and it's fun. It's great. Love that. And basically, you get BTUs, which is mainly used for combustion, but my PowerPoint part is going to have to do with a lot of BTUs. Just know that it takes 3,412.14 BTUs for 1 kilowatt hour. What does that mean? Well, go to the next slide. Here are some ways that you can think about that. A ceiling fan is 150 watts, which means that it's about 511 BTUs. So just so you can relate it to something. We have the apple seed reactor over here, half our holding tank, but just ignore that. And I took into account the pump and the heating component that we have attached to it. And it equals about 16,695 BTUs. So that is BTUs in a nutshell. I put some costs, how many hours, if you run both for 2 hours, just so you can get a grasp of that. All right, so why is it important to balance your shop? Well, if you have a commercial biodiesel shop and if you're selling biodiesel, you obviously know how much energy and how much money you're putting into making your fuel, so you know how much to charge it at. So cost analysis is definitely important. I do some cost analysis for the Dickinson biodiesel shop. So that works in well with energy balancing, of course. Research opportunities that I'm working on. Research opportunities, we are a research shop, so balancing the shop gives, like me, a chance to play around with BTUs and kilowatts and all the equipment in the shop that I'm getting introduced to, and it's great. Figure out how we can reduce the amount of energy we're putting into the system while increasing the amount we're getting out. Yeah. And then fuel efficiency, like I said, how much energy we're putting in compared to how much we're getting out. That should be switched, output, input, because the higher number you have for that ratio, the better your energy balancing is. So here, this is the electrical equipment that we have in the shop, volt amps and wattages. So, I don't know what you know about volt amps, but just to briefly explain, it is volts times amps. It's pretty simple. at least on this level. Each machine contains a certain amount of volts, a certain amount of amps, runs at that. Multiply them together, and you should have wattage. But as you can see, the wattages for most of these pieces of equipment are about 65% less, minus the heating component. This is because of the AC current that they are using. AC current, you know, it oscillates. So this is the average amount of wattage that you're using at any given time. All right, and this is the material input. This is all the material that goes into the process. I didn't include water because I'm not including that in any of the cost or energy analysis that I'm doing at the moment. We have no way of measuring how much water that we're putting into the system, like when we wash the fuel. That's a consideration for the future. But right now, this is how much we're paying for each of these materials. Gasoline is just to go pick up the waste vegetable oil, which is free for now. There are already restaurants in other places in our town that's charging. So hopefully we can just, yeah?
How come you didn't have a BTU factor for the recovered methanol if you were using energy to
Recover it.
recover it?
I didn't include BTUs for that because I'm putting the energy that we're using to recover this methanol. I counted for in the last batch. I haven't included it for future batches, like if we were to use a recovered methanol from one batch in another. I'm not including that right now because this is still at a basic level. I'm not completely literate in embedded energy yet. I only have a simple knowledge on that right now. So I'm going to explain what I know about it. Yeah, just because I don't know that much about embedded energy right now, for the most part. So, yeah.
Then we're measuring the cost of our fuel, and we're treating the glycerin as something separate because we're looking more into soap production, and so we're going to factor that into our energy costs for soap production when we get a better handle on that.
Yep. Just so you know, in this presentation though, like I have not taken into account anything with glycerin. Anything you see pertaining to methanol or anything I say, I'm not taking into account the methanol that we're getting back from the glycerin. It's just the biodiesel. So and I'm also, just to clarify, I guess, I'm not taking into account any costs when it comes to titration materials, labor costs when it comes to our research, putting together these presentations, just direct labor costs like doing the process or like clicking the switch, making sure everything's running. But embedded energy with BTUs, we still have to do more with. So embedded energy, this is what I know. The figure I gave earlier for the amount of BTUs per kilowatt hour is the amount that you're going to get charged for by the electrical companies. But you actually use a lot more. You actually use about 3 times that because as energy goes through, or as electricity goes through the wires and into your shop, it loses some energy through friction, and you lose it to like, I don't know, you just use energy to different sources. So you actually have to use a lot more energy than basic calculations will give you. So you have to take that into account because even though you're not getting cost or charged for it, you are using extra energy. So that's electrical energy. Energy costs for methanol, and then why? It's the cost for making the methanol and making the lye that we buy. Because someone somewhere is making that material, there's energy going into making that material, and then we're using it to make a final product, which is why we should be taking into account the BTUs of methanol we're recovering. Just haven't done that yet. But yeah, we do take into consideration the BTUs of embedded energy for these 3 material inputs, and for electricity, but that's it right now. All right, so this is some really, really basic equation that hopefully I didn't get wrong, but it has to do with the amount of energy we're getting from our solar thermal heating system. We're using it to preheat the oil before it goes into the Appleseed reactor. That way we don't have to keep the heat on too long before we actually do transesterification. Saves us energy, saves us costs, and it's great. We also can do research with the solar panel. But this right here is an equation to figure out how much energy we are saving. Delta Q equals M delta T C. Basically, it means the amount of energy you're getting is equal to the mass of whatever you're measuring, times the temperature change, times the specific heat. We have 6 gallons of 50/50 antifreeze in the thermal heating system that circulates. So to figure out the mass, you should be using a rate at which the antifreeze is recirculating.
Why do you use antifreeze instead of glycerol?
Instead of glycerol? We just haven't considered that, I guess. I don't.
With glycerol, below ambient temperatures, it freezes, or well, it gels up. So especially using it in the winter, in between the line, well, especially in the heat return, it will gel up and clog very quickly.
The system was already set up when I got here, so. But yeah, okay, so we have 6 gallons going through the system. You should be using a rate at which it's actually circulating. We haven't been able to do that yet, so we have the volume. We just needed the density to figure out the mass. I found a density online for 50/50 antifreeze. So this is really rudimentary, like first time we figured out this calculation. So just so you know. But we figured the mass to be 2.42 kilograms. There's a temperature change. We used a Hobo data collector and set 2 sensors to the input and to the output of the thermal system to figure out what the temperature change is, and it was about 35 degrees Fahrenheit, so 1.6 degrees Celsius. And then this is the specific heat of 50/50 antifreeze. You can see it's in joules per kilogram Kelvin. The fact that specific heat is in Kelvin and the temperature change is in Celsius is fine. It's the same scale, so it doesn't matter. And then we just figured out what the energy we're getting out is, and it's about 13,000 joules, or 12.23 BTUs every time it circulates through. The 6 gallons circulates through the system. So, saving on energy for methanol recovery. Doing methanol recovery, you use more energy. You have to keep the biodiesel, glycerin also, you do it on the glycerin. You have to run it through the pump, but you also save on a lot. We pay about $4.10 per gallon. So for every gallon that we get back that we can reuse, if it's above 95%, we save on $4.10. And we save on whatever the embedded BTUs are if it costs us less BTUs in the process. So yeah. All right, so this one's right, output, input. This is our analysis. As you can see, batch 2 and 3 are empty. It's very important to have good records because this is what happens when you don't. But for everything else, we did have records for. Batch 7, we came in one day, little bit of a spill, about 54 gallons. So we also don't really have an output for that, although it did cost us $219. But everything else is pretty normal. Our average output versus versus input is about high 4, which is really good. I guess the average right now for commercial is about 3.2 to 1. Ours is high because the fact that we're using waste vegetable oil. There are no BTUs, embedded energy, associated with that because that technically is the loss of the people who are giving it to us, and it's our gain. And then also, for some reason, I found the embedded BTUs of KOH and NaOH online. We need to refine those a little better, make sure that they're more accurate. But for some reason, NaOH had a lesser value. So anything with NaOH had a better output versus input ratio. So I don't know if that's exactly accurate or not, but the average is about high 4 for our shop.
Question
All right.
on that.
Yeah.
What previous chart? Your outputs are all the same.
Yes.
What is your units of volume, or what is it?
Yeah, we have an output of about 45 gallons, or to 50 gallons.
Are you asking for the BTUs?
These? Oh, these are BTUs, yes, sorry.
Yeah.
So that's the BTUs for about 45 gallons. And we do have an output about that. It fluctuates a little, maybe like 53 or 43, 46. We have no way to exactly measure that right now, but it is about an average of 45. So that is BTUs for 45
Okay.
gallons.
I was just curious why they were all the same.
Yeah.
It's because the batch size is the same.
Yeah.
Okay.
All right, so $2.07 per gallon is our average right now. And a way to decrease this is to increase our batch sizes. Right now, it's mainly a research shop, like we've said before. If we got better equipment, we could increase our batch sizes, maybe decrease our costs overall. Of course, fixed costs need to come into play, but I haven't really presented anything about fixed costs. I haven't really analyzed anything of that yet. Differentiating between new methanol and recovered methanol. This is where the embedded BTUs come into play again. Does it cost less energy for us to recover our methanol than it is to just buy the methanol? It is cheaper, but does it cost less in energy? We haven't studied that entirely. That is a research opportunity available for us in the future, for future interns, anyone who wants to come by. And then also buying materials in bulk. We don't buy our NaOH in bulk yet. And it costs a lot. It costs about 8 something per kilogram right now. If we were to buy in bulk, it would be less, along with some other things. So right now we don't do that because we don't make large batches. And then considerations for the future. Better record keeping. As you can see, batch 2 and 3 of this summer, all those batches were just this summer, had no information. We just need to make sure that we have correct batch sheets. Everything we want to know is on the batch sheet so someone can fill it in. We also have to make sure people are filling in the information. So that way we can do this analysis more accurately, more often. Embedded energy and recovered methanol, I keep coming back to this. It is very important that we figure out how much energy we're using to recover methanol. We don't have yet. And then kind of pertaining more to the methanol recovery portion of this presentation, a reflux column on the glycerin. That way we can get pure methanol back from the glycerin recovery as well. We haven't done much energy or cost analysis on anything pertaining to glycerin yet. Anything we have done, we haven't really presented here. It's more understudy still. We're basically doing it for our soap marketing right now. Yeah, that's the end of our slide.
Questions?
Questions?
What you have on this sheet right here is you're talking about methanol recovery from the biodiesel fuel. Not the glycerin?
This is, our boss Matt Steinman put this together about a year and a half ago. The purpose of that is a primer, just to introduce people to the concepts of methanol recovery. We're going to be working on later this summer, coming up with a conclusive how to do it, what prices to expect, what equipment you need. So that way, we're hoping to put on the biodiesel column.
Do you have that ready, or you're
We're writing it.
Is there any information on the reflux skill? How to make it?
Or can you just go back to that slide? So the reflux column is, what we have is for an in-column apple seed reactors in the parts list right here. The main part of this reflux column is just a 2-inch, 2-inch by 30-inch nipple, which the price is, this entire set we bought off the MSC for this price. And with that nipple, you then place the copper scrubbies inside to create your surface area. And then you have the 2-inch down to 3/4 coupling. Most water heaters are 3/4 on their exhaust. So you can just throw it into place. The T's that are included are for when you're putting in the Pasco thermometers ordered through Utah Biodiesel. And it honestly it's that easy and simple to build.
So is the top open or is that plugged as well?
The top is connected to our exhaust system, where we have the option of for recovery and for venting.
So it just vents out, it doesn't have a top-off valve or something?
Yeah, it's not really pictured, but there is a pressure release valve directly above it.
So it just goes up and the vapor just turns back there and goes across?
And it can go down through the condenser, or it can go right out to the shop. So we use the condenser for when we're doing recovery, but when we're loading and emptying the reactor, we emit the outside air.
The water cooled reactor there?
Yep.
If you're looking for more information on reflux columns in general, the basic principle is just fractional distillation. You can easily find a very easy to read explanation on Wikipedia or just doing a Google search. But I primarily base this off of ethanol distillation because it's sort of similar. It's more complicated because you get a mixture of these liquids that will boil off at a constant boiling point, and you won't have the separation of boiling points like you do here with methanol. But that's basically where I took the design from.
Did you guys consider doing it under vacuum?
We have, but we felt that we have to purchase additional equipment to do it, and there's one set up. We felt that it'd be more efficient to using just heat distillation.
So cost effective probably wouldn't be as much.
We haven't really looked into pricing, but what we've been told is to buy a vacuum rated pump, and especially to make sure everything is vacuum rated, it would just be more expensive to buy additional equipment and work it in, and we felt that the man hours and the equipment was just unnecessary.
But it's definitely something to look into. It might make your recovery better.
A question and a comment. The question first off is, why are you not recovering water at the bottom of your reflux column, just getting rid of it rather than mixing it back with the glycerin in the tank? And the comment is that you said you just kind of, it sounded like, run this till you think you're done getting rid of your methanol?
Well, for biodiesel, we run it until there is no further vapor pressure, until there is nothing left coming off. And then for methanol, or for glycerin, we only take it off to 260 because that's the highest we feel comfortable with taking it so far. We can take it higher,
But after doing a flashpoint test on the glycerin that was taken up to 260, we're fairly confident that most of the methanol is gone.
And what I was curious about though is, you're not insulated on your pipe, but if you were and you had accurate thermometers on top and bottom, your temperature gradient should go away when you're done with the two-phase and just have a single.
It does the temperature gradient does disappear with biodiesel when it no longer recovers.
So that should tell you, I mean, that should be the same, I think, with the glycerin as well. When the water is still there, but the methanol is gone, your gradient should go away.
But as to why we don't take out the water, at the moment, I can't think off the top of my head a way to take the water out at that point without having, because if you have an opening at that point, the methanol will push itself out because it travels less and the path of least resistance. I'm not sure, I'd have to talk to someone who can know that.
I think if you had like at the bottom of your system there, if you had a ring that would capture the water that's coming down the column on a tube coming out, and then just a water check in it, depending on how much pressure you build up, to tell you how tall that has to be, and you could solve that problem, I think.
Well, also for what we're doing with our glycerin, it doesn't really matter that it has water in it because we're mainly adding water to it. In terms of using it for compost, using it to make soap, and even with the biogas digesters, we're putting water back into it. So we're not really trying to, clean it up and sell it. Which, if we were trying to do that, it would make sense to try to get the water out and then get other impurities out. But that's definitely going to cost us a lot of money.
Okay.
Have you considered cooling the reflux?
We have, my concern is that if we start cooling it, it might not even allow the methanol to escape. And so right now, leaving it ambient temperature exchange, it's creating the perfect stratification of temperature, and at this point, it's just my fault of why fix something that's not broken.
Do you have any sense about maintenance as to when or if you'll have to change out the copper pads?
We're